Hey, Mark.
Hey, bud. Hey, what you working on there?
Hey, Mark. I'm just working on some heat and mass. You want to give me a hand?
I don't know. I'm pretty parched. I don't think I can do heat and mass right now. I need something to drink first.
Have yourself a pop.
Yeah, I can try it. Let's see, our mist is really warm. I don't really want this right now.
Put it in the freezer for a little bit.
Freezer? All right.
Cool it down.
Guess that could work.
A few moments later.
You know, I think your pop will be ready now.
Oh, yeah, probably right. It's been for a few minutes. Oh, man. Pop still's like kind of warm still.
Really?
Yeah, I don't know. Not that great.
What else could we do?
I don't really know.
I got it! For our experiment, we want to find a fast way to cool down a can of pop. The three methods we thought of to do this are a freezer, a bucket of ice water, and a bucket of ice and salt water. To simulate this, we have a can with air, a can with water, and a can with salt water. And these will be our containers that we use to hold our pop cans. These containers are used to keep consistent geometry for our experiment. These cans will be kept in a bucket of ice water, and the bucket acts as our 0 degrees Celsius heat sink.
From this experiment, we will learn why Mark was disappointed with the temperature of his pop can at the beginning of the video.
In order to do this experiment, we're going to need the following things. 3 mini pop cans, 3 larger Arizona iced tea cans, tape, and scissors to make the holes in the Arizona iced tea cans to make them workable for the experiment, a ruler to measure various lengths, a thermometer to measure all the different temperatures during the experiment, and finally, a large container that contains ice for our heat sink.
The theory to our experiment is as follows. The geometry is one cylinder contained within another cylinder in a surrounding medium. The length and radii are as shown. Both cans are aluminum, with the inner can being filled with soda and our variable media in between them. Our materials have the following thermal conductivities. Our initial temperatures and desired delta T values are also shown. Our governing equation is heat transferred is equal to temperature change over total resistance, with the total resistance being the sum of the inner can, fluid, and outer can resistances. The resistances are solved for radial heat transfer in cylindrical coordinates. Solving for Q, we can predict which media will allow the most heat to transfer and therefore faster cooling. From this, we expect the fastest cooling from salt water, then air.
Alright, so now we're actually going to run the actual experiment, and what we're going to be doing is, like we already mentioned, we're going to be placing these cans of soda into 3 different Arizona cans that have different cooling mediums in them, one with air, one with water, and one with salt water. And the way we're going to run this experiment is what we're first going to do is open up the cans of soda and measure the inside temperature before we place them in the heatsink. And once we've got the calculated beginning temperatures, which should be room temperature, we're going to be placing the open cans of soda into the Arizona cans that have the mediums in them, like this. And then we're going to be placing them in our heatsink to cool them off for the same amount of time. We're going to place each of these cans of soda in there for 2 minutes. And then once the 2 minutes have run out for each of these each of these Arizona cans, take them out and measure the inside temperature again of the soda. And what we'd expect is, from earlier on in the video, whichever medium has the highest Q value should be the soda that has the greatest temperature difference, or should be the coldest.
First, we measure the temperature of the warm can. Initial temperature of 68.8 degrees Fahrenheit. The pop cans are loaded into their respective cans. Each can is then placed in the tub for 2 minutes, then removed and its temperature is measured. Our initial soda temperature was 68.8 degrees Fahrenheit. The smallest temperature change was in the soda and air, with a final temperature of 65.9 degrees Fahrenheit after 2 minutes. The second smallest temperature change was in the soda and water, with a final temperature of 58.3 degrees Fahrenheit after 2 minutes. The largest temperature change was in the soda and salt water, with a final temperature of 51.9 degrees Fahrenheit after 2 minutes. This matches our prediction, with the highest temperature change correlating to the highest Q value.
The results of our experiment confirmed our hypothesis that a bucket of salt and ice water would get your can of pop cool the quickest. Second place would be for a bucket of ice water, and the slowest way would be to take your can of pop and put it in the freezer. As we have shown, chemical engineering principles like thermal conductivity can be used to solve everyday household problems. And that's pretty cool.